Welcome to the Mathematics MI channel. In this video, we are going to evaluate this integral 0 to infinity x square over x to the fourth power minus x square plus 1 raised to the n power times 1 over x square dx. Okay, I think this function familiar with you. This is we know rational function x square here fourth power x square. So if we take x is equal to 1 over u substitution, we know we will have the same function after substitution. So I am going to take that substitution. We can take x is equal to 1 over u. Now differentiate dx is equal to minus 1 over u square du. Then we can plug in here. We can take this is I, and we know now I is equal to, now we should change the boundaries when x approaches to 0. We know here infinity, here 0. Now x square we know 1 over u square, so 1 over u square over x to the fourth power we know 1 over u to the fourth power minus 1 over u square plus 1 raised to the n power times here dx we know minus 1 over u square du over here x square we know 1 over u square. So we know 1 over u square get cancelled, and here we can change this boundary 0 to infinity. When we change the boundary, this minus get cancelled, and here we can simplify. So if we take common denominator here u to the fourth power, so this u square get cancelled, and we will have u square in the numerator. So here u square over, now here u to the fourth power, so I am going to write it first. So u to the fourth power minus u square plus 1 raised to the n power times here only du. Okay, then we can change the variable here 0 to infinity. Now instead of u I am going to take x, because definite integral independence of the variable. So here x square over x to the fourth power minus x square plus 1 raised to the n power dx. We know this is also equal to I. Okay, then I am going to take sum of these integrals. So 2 times I is equal to integral from 0 to infinity, same boundary, and we know this part is a common factor, so we can write x square over x to the fourth power minus x square plus 1 raised to the n power times, now here 1 over x square, here 1, so 1 plus 1 over x square dx. Okay, then we can simplify this is like here 0 to infinity. Now I am going to divide it by x square. So here we have 1 over here x square minus here 1 over x square, so plus 1 over x square, here minus 1. Now we know here this is raised to the n power, and here also we have 1 plus 1 over x square dx. Okay, then we can write here 2 times I is equal to now to evaluate this integral I am going to use a substitution. We know the substitution is x minus 1 over x is equal to t. So x minus 1 over x is equal to t. Then differentiate 1 plus 1 over x square dx is equal to dt. Also if we take 2 power both sides, so here x square plus 1 over x square minus 2 is equal to t square, so this is equal to t square plus 2. So now we can write here 2 times I is equal to integral, now limit we know when x approaches to 0, here minus infinity, so minus infinity to infinity. Now 1 over x square plus 1 x square we know t square plus 2, here minus 1, so t square plus 1 raised to the n power, and 1 plus 1 over x square dx we know dt. So here dt. Okay, now we have 2 times I. Now according to symmetry we can write I is equal to 0 to infinity. Here 2 times and here 2 get cancelled. Dt over t square plus 1 raised to the n power. Okay, now how to evaluate this integral? Okay, if we take t is equal to tan of theta, we know 1 plus tan square of theta, secant square of theta. Here if we differentiate also secant square of theta, and we can simplify this is like here. Now I am going to take t is equal to tan of theta, then we know dt is equal to secant square of theta d theta. Okay, then we can plug in here. Now limit we know 0 to tan of infinity, so here pi over 2, and dt is equal to secant square of theta d theta over t square plus 1, we know tan square plus 1 secant square of theta, so here secant of theta raised to the 2n power. Okay, then we can simplify this is now here 0 to 5 over 2, we know this is equal to cosine to the 1 over secant, we know cosine to the 2n of theta, and here secant square of theta, so we can write cosine raised to the 2n minus 2 of theta d theta. Well, now this is familiar with us. We evaluated this type of integrals many times, so now we can use, we know, beta function. So here we know we can write this is equal to 1 times 1, we know sine raised to the 0 power of theta cosine to the 2n minus 2 of theta d theta. Okay, then we know about beta function integral. Beta of mn is equal to integral from 2 times integral from 0 to pi over 2 sine raised to the 2m minus 1 of theta cosine raised to the 2n minus 1 of theta d theta. Okay, then so we can rearrange our integral. I is equal to integral from 0 to pi over 2, here sine of 2 times 1/2 minus 1 of theta, here cosine raised to the 2 times 2n minus 1 over 2 minus 1 of theta d theta. Okay, then we can apply this formula, so we can write now this is equal to 1/2 beta of 1/2 comma 2n minus 1 over 2. Now we know we can write beta function by using gamma function. So beta of xy, we know beta of xy is equal to gamma of x gamma of y over gamma of x plus y. So we can write here gamma of 1/2 gamma of 2n minus 1 over 2 over gamma of 1/2 plus 2n minus 1 over 2. Okay, then we know gamma of 1/2 is equal to square root of pi, so square root of pi over 2 times gamma of 2n minus 1 over 2 over gamma of, if we simplify this, 1 minus 1 get cancelled, 2 also get cancelled, here gamma of n. Okay, this is the answer. If you like this type of videos, please subscribe this channel. Thank you for watching.